Let's start with part 2 of Human Eye and the Colorful World. Refraction of light through a prism. You've learned how light gets refracted through a rectangular glass slab. For parallel refracting surfaces, as in a glass slab, the emergent ray is parallel to the incident ray. However, it is slightly displaced laterally. How would light get refracted through a transparent prism? Consider a triangular glass prism. It has two triangular bases and three rectangular lateral surfaces. These surfaces are inclined to each other. The angle between the two lateral faces is called the angle of the prism. Let us now do an activity to study the refraction of light through a triangular glass prism. Fix a sheet of white paper on a drawing board using drawing pins. Now place a glass prism on it in such a way that it rests on its triangular base. Trace the outline of the prism using a pencil. Draw a straight line PE inclined to one of the refracting surfaces, say AB, of the prism. Fix two pins, say at points P and Q on the line PE as shown here. Look for the images of the pins fixed at point P and Q through the other face AC. Fix two more pins at the points R and S, such that pins at R and S are the images of the pins at P and Q lie on the same straight line. Join and produce the points R and S. Let this line meet the boundary of the prism at F. Now remove the pins and the glass prism. Join E and F. Now draw perpendiculars to the refracting surfaces AB and AC of the prism at points E and F respectively. Mark the angle of incidence as angle I, the angle of refraction as angle R, and the angle of emergence as angle E as shown here. Here PE is the incident ray, EF is the refracted ray, and FS is the emergent ray. You may note that a ray of light is entering from air to the glass at the first surface AB. The light ray on the refraction has bent towards the normal. At the second surface AC, the light ray has entered from glass to air. Hence, it has bent away from the normal. Now compare the angle of incidence and the angle of refraction at each refracting surface of the prism. Is this similar to the kind of bending that occurs in a glass slab? The peculiar shape of the prism makes the emergent ray bend at an angle to the direction of the incident ray. This angle is called the angle of deviation. In this case, angle D is the angle of deviation. We can mark the angle of deviation in the activity and measure it. Did you find this activity interesting? Let's move on to our next topic, which is dispersion of white light by a glass prism. You must have seen and appreciated the spectacular colors in a rainbow. How could the white light of the sun give us various colors of the rainbow? Before we take up this question, we shall first go back to the refraction of light through a prism. The inclined refracting surfaces of a glass prism show exciting phenomena. The angle between its two lateral faces is called the angle of the prism. Let us now do an activity to study the refraction of light through a triangular glass prism. Take a thick sheet of cardboard and make a small hole or narrow slit in its middle. Allow sunlight to fall on the narrow slit. This gives a narrow beam of white light. Now, take a glass prism and allow the light from the slit to fall on one of its faces as shown here. Now, turn the prism slowly until the light that comes out of it appears on a nearby screen. What do you observe? You will find a beautiful band of colors. Why does this happen? The prism has probably split the incident white light into a band of colors. Note the colors that appear at the two ends of the color band. What is the sequence of colors that you see on the screen? The various colors seen are violet, indigo, blue, green, yellow, orange, and red, as shown here. The acronym WIPCURE will help you to remember the sequence of colors. The band of the colored components of a light beam is called its spectrum. You might not be able to see all the colors separately, yet something makes each color distinct from the other. The splitting of light into its component colors is called dispersion. You have seen that white light is dispersed into its seven color components by a prism. Why do we get these colors? Different colors of light bend through different angles with respect to the incident ray as they pass through a prism. The red light bends the least, while the violet the most. Thus, the rays of each color emerge along different paths and thus become distinct. It is the band of distinct colors that we see in a spectrum. Isaac Newton was the first to use a glass prism to obtain the spectrum of sunlight. He tried to split the colors of the spectrum of white light further by using another similar prism. However, he could not get any more colors. He then placed a second identical prism in an inverted position with respect to the first prism, as shown here. This allowed all the colors of the spectrum to pass through the second prism. He found a beam of white light emerging from the other side of the second prism. This observation gave Newton the idea that the sunlight is made up of seven colors. Any light that gives a similar spectrum to that of sunlight is often referred to as white light. A rainbow is a natural spectrum appearing in the sky after a rain shower. It is caused by the dispersion of sunlight by tiny water droplets present in the atmosphere. A rainbow is always formed in a direction opposite to that of the sun. The water droplets act like small prisms. They refract and disperse the incident sunlight, then reflect it internally, and finally refract it again when it comes out of the raindrop, as shown here. Due to the dispersion of light and internal reflection, different colors reach the observer's eye. You can also see a rainbow on a sunny day when you look at the sky through a waterfall or through a water fountain with the sun behind you. Next is atmospheric refraction. You might have observed the apparent random wavering or flickering of objects seen through a turbulent stream of hot air rising above a fire or a radiator. The air just above the fire becomes hotter than the air further up. The hotter air is lighter than the cooler air above it and has a refractive index slightly less than that of the cooler air. Since the physical conditions of the refracting medium are not stationary, the apparent position of the object, as seen through the hot air, fluctuates. This wavering is thus an effect of atmosphere refraction, that is, refraction of light by the Earth's atmosphere, on a small scale in our local environment. The twinkling of stars is a similar phenomena on a much larger scale. Let us see how can we explain. The twinkling of a star is due to atmospheric refraction of starlight. The starlight on entering the Earth's atmosphere undergoes refraction continuously before it reaches the Earth. The atmospheric refraction occurs in a medium of gradually changing refractive index. Since the atmosphere bends starlight towards the normal, the apparent position of the star is slightly different from its actual position. The star appears slightly higher or above than its actual position when viewed near the horizon. Further, This apparent position of the star is not stationary but keeps on changing slightly, since the physical conditions of the Earth's atmosphere are not stationary. Since the stars are very distant, they approximate point sized sources of light. As the path of rays of the light coming from the star goes on varying slightly, the apparent position of the star fluctuates and the amount of starlight entering the eye flickers. The star sometimes appears brighter and some other time fainter, which is the twinkling effect. Now, if we ask, why don't the planets twinkle? Well, the planets are much closer to the sun and are thus seen as extended sources. If we consider a planet as a collection of a large number of point sized sources of light, the total variation in the amount of light entering our eye from all the individual point sized sources will average out to zero, thereby nullifying the twinkling effect. Pretty interesting, right? Now let's see advanced sunrise and delayed sunset. The sun is visible to us about 2 minutes before the actual sunrise and about 2 minutes after the actual sunset because of atmospheric refraction again. By actual sunrise, we mean the actual crossing of the horizon by the sun. In the figure here, see the actual and apparent positions of the sun with respect to the horizon. The time difference between the actual sunset and the apparent sunset is about 2 minutes. Also, the apparent flattening of the sun's disk at sunrise and sunset is also due to the same phenomena. Hope you are good till now. Let's now know about scattering of light. The interplay of light with objects around us gives rise to spectacular phenomena in nature. The blue color of the sky, color of water in deep sea, the reddening of the sun at sunrise and the sunset are some of the wonderful phenomena we are familiar with. In the previous class, you have learnt about the scattering of light by colloidal particles. The path of a beam of light passing through a true solution is not visible. However, its path becomes visible through a colloidal solution where the size of the particles is relatively larger. Next is Tyndall effect. The Earth's atmosphere is a heterogeneous mixture of minute particles. These particles include smoke, tiny water droplets, suspended particles of dust, and molecules of air. When a beam of light strikes such fine particles, the path of the beam becomes visible. The light reaches us after being reflected diffusely by these particles. The phenomena of scattering of light by the colloidal particles gives rise to Tyndall effect, which you have studied in class 9. This phenomena is seen when a fine beam of sunlight enters a smoke filled room through a small hole. Thus, scattering of light makes the particles visible. Tyndall effect can also be observed when sunlight passes through a canopy of a dense forest. Here, tiny water droplets in the mist scatter light. The color of the scattered light depends on the size of the scattering particles. Very fine particles scatter mainly blue light, while particles of large size scatter light of longer wavelengths. If the size of the scattering particles is large enough, then scattered light may even appear white. Pretty interesting, right? Now let's move on to our last topic from this chapter, which is why is the color of the sky blue? The molecules of air and other fine particles in the atmosphere have size smaller than the wavelength of visible light. These are more effective in scattering light of shorter wavelengths at the blue end than that of longer wavelengths at the red end. The red light has a wavelength of about 1.8 times greater than that of blue light. Thus, when sunlight passes through the atmosphere, the fine particles in the air scatter the more than the strongly blue color more strongly than the red color. The scattered blue light enters our eyes. If the earth had no atmosphere, there would not have been any scattering. Then the sky would have looked Dark. The sky appears dark to passengers flying at very high altitudes as scattering is not prominent at such heights. You might have observed that danger signal lights are red in color. Do you know why? The red is least scattered by fog or smoke. Therefore, it can be seen in the same color at a distance. With this, we come to an end of this wonderful chapter. If you like the video, consider liking, sharing, and subscribing for more. Have a good day. Bye bye.